Hello, everyone. My name is Keyvan Ghanbari. I am currently a postdoctoral research assistant at the University of Alabama in Huntsville, the Center for Space Plasma and Aerodynamic Research, CSPAR, and the Department of Space Science. I am very happy to have the opportunity today to uh, uh, give a presentation about my research here. As a very quick background, I got my I come from Iran. I got my bachelor's and a master's degree back in Iran in theoretical and astrophysics, theoretical physics and astrophysics. And then I got a master's in cosmology. And then I moved to the US um, in 2017, and I started my PhD program here in this department, uh, working with Dr. Vladimir Florinsky. I got my PhD in 2022 March, and I had the honor to work for Dr. Gary Zank as a postdoc uh, on the research that I'm going to present for you today, entitled "Studying Collisional and Weakly Collisional Shock Structures in the Very Local Interstellar Medium." As an acronym, LVISM will be used for this whole word. So let's see what this talk will be composed of. The outline of my talk will be a quick description of a shock and also uh, the kind of definition of the shock in our context, in the space plasma context, um, the sources of these shocks that we see in the space plasma and the propagation processes in this context again. I will also give you a very quick uh, examples of the shocks that are uh, in the space and those that are observed in the very local interstellar medium, LVISM. And then I will move on to uh, how we try to describe these space plasma around these shock structures and how we use uh, fluid models with higher order moments. And what are these moments? I will give a description of those, and then I will talk about the collision processes and how the collisions will affect the behavior of these shocks. And then finally, I will talk about the significance and applications of this study, and then a summary of this presentation. So let's get to it. What is a shock? Um, Normally, in the nature and physics, we define a shock uh, as a disturbance that is moving, that is traveling with a speed higher than the speed of sound in the medium that it is in. Uh, Very famous form of shock is something that you have all probably seen, is the kind that forms in front of a fighter jet when the fighter jet uh, 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 moves with a speed higher than the speed of sound. Um, in physics, we define the speed of sound as with the equation, with the relation that is shown in the on top left of the screen as the square root of gamma ktm. This is speed, depends on the temperature of the medium, depends on the mass of the components of the medium. Gamma is the ratio of the specific heats, which is another important physical parameter, and K here is the Boltzmann constant. Normally, to describe um, the speed of the shocks, we use a dimensionless factor, dimensionless parameter called Mach number, which is actually the ratio of the speed of the disturbance uh, to the speed of sound in that medium. Obviously, when this Mach number uh, or the speed Mach number is less than 1, we call the motion as a subsonic. When the Mach number is equal to 1, the motion is called sonic. And when the Mach number is greater than 1, the disturbance moves with a supersonic speed. very nice. This kind of illustration is shown on the right of the screen. The sources of the shocks that are observed in the space um, plasma, specifically in the solar wind, are shown here. As we know, as you all may know, the solar wind comprised of 90% protons and around 8% helium ions, and then some heavy ions after them. Uh, Constantly emanates from the sun with average speed of 400 kilometers per second, uh, which in this medium, the speed of sound becomes 100 kilometers per second. Um, because of the nature of the sun, um, uh, due to some transient and small and large scale structures generated in the solar surface, such as coronal mass ejections or solar flares or co-rotating interaction regions. Uh, these shocks can be generated and they can be propagated in the solar system, and they, depending on their strengths, they can uh, travel all the way towards the boundaries of the outer boundaries of the solar system. Some naturally formed uh, shocks in the solar system, or in our terminology, in the heliosphere, and its interaction with the interstellar medium, are termination shock and heliopause that are basically caused by the fact that the solar wind uh, that is traveling with a supersonic speed uh, turns subsonic at the termination shock, which is shown in the figure, the bottom figure of the right panel. And heliopause is basically the boundary between the solar wind um, dominated region and the interstellar medium. The shocks that are generated at the sun and they propagate outward in the solar system, they can interact with each other. They can interact with the heliosphere, termination shock, and heliopause, and become even more complicated structures. Um, one of the things, one of the main things that we do in science is trying to understand how these structures, how these events work, um, how we can describe them physically. Another source of shocks are rotating interaction regions. That picture, a schematic picture of this. This structure is shown in the center bottom panel that has a forward and reverse shock. Here, actually, I'm showing the kind of a large-scale picture of the heliosphere and the neighboring interstellar medium. The boundaries between our solar system and the outer interstellar medium, the termination shock, the heliopause, are shown here, and the two very well-known spacecrafts that the Voyager 1 and 2 that are in the interstellar medium currently, and they are still transmitting data to us. This is actually a very nice video of the location and some information about the Voyager 1 and 2 spacecrafts and how they are located in the space in with respect to the solar system with respect to sun. And you can see that yeah, this is Voyager 2 right now. It's shown in the movie on the left panel, and then this location with respect to the solar system, and then this is the solar system. And if we go zoom in, this is the heliosphere or inner solar system that shows the sun and the closer planets to that. And then we will move on to the location of the Voyager 2, and then we can look at the location of the Voyager 1 spacecraft and its positioning, its location with respect to the solar system. These two spacecrafts that were launched in 1979, they crossed the heliosphere termination shock in 2004 and 2007 at around 94 AU astronomical units, 94 and 84 astronomical units, and then they crossed the heliopause in 2012 and 2018 at around 121 and 119 astronomical units from the sun. Shocks in the LVISM. According to the data collected by these two spacecrafts, we know that some of these shocks that are generated at the sun, they can penetrate deep into the interstellar medium, and we have evidence for that in the Voyager 1 and 2 data. On the very left panel, you can see the Voyager 1 collected data and the duration of 2000 during the time of from 2012 to 2022, and the heliopause HP is marked with a solid vertical line, and then there are two shocks that are marked in there. The middle panel shows the Voyager 2 data from 2018 to 2021, and the crossing of this spacecraft from heliopause and the shock that was observed in 2020. And in the left panel, we can see the Voyager 2 observations from its crossing from the termination shock in 2007. So Voyager 1 observations. I mentioned the previous slide that there were two shocks observed by Voyager 1 in 2012 and 2014 that had different features from the shocks that are observed in closer to the sun in the inner heliosphere. Some of these features are the increase in which is the magnitude of the magnetic field, the weaker shock ratio in comparison to the shocks that we see in the closer to the sun, and also the thickness of these shocks that are comparably different from those shocks that we see closer to the sun. The shock thickness observed by the Voyager 1 spacecraft is 10 to the power of 4 rather than the shocks with similar properties at the 1 astronomical unit closer to Earth orbit. So let's see how we can understand these structures and how we can basically define the space plasma around these structures. For that, there are many models that are developed to describe the physical properties of the space plasma around these systems, around these structures. But by physical properties, what I'm talking about is the properties such as density, velocity, pressure, and some other properties that you already use in your daily life. For example, we measure the density of the air. I don't know the velocity of the air particles, or in other words, we measure the wind speed. I don't know, and then the pressure of the air, or the pressure of the molecules in a chamber. We use these physical properties to define the behavior of the components of for example, a system. One of the most important equations that are used to describe this the physical behavior of the system is called the Boltzmann equation. And this equation, which is shown at the second line, the left equation, the time variations of the distribution of the particles depends on the forces acting on those particles, the diffusion of those particles, and all the collisions that are happening in between the particles in that system. In a more mathematical way, in a more physical way, this equation is opened up and written in the form that is shown in the second line on the left. Using this Boltzmann equation, we can obtain the evolution equation for all of these physical properties of the system that we have. Magnetohydrodynamic theory is one of the most well-known theories that is used to study the behavior of these physical properties, which uh, is formed by three main equations, which is the equation of the continuity, or the mass density conservation, the momentum conservation equation, and the energy conservation equation, which are shown in the conservation laws, plus the Maxwell equations. Um, we also have the we also use some of the approximations um, to make the system easier for us to evaluate. In one of these models, which is another well-known model, it is called Navier-Stokes model, and in this model, the pressure tensor, which appears in the appears in the momentum conservation law and the energy conservation law, the pressure tensor is written in the form of scalar pressure and a stress tensor, which is shown in the bottom right panel. And there is another physical factor called heat flux that comes into the equation of the in the Navier-Stokes model. That physical property, heat flux, which is shown as Q, is written in the form of the derivatives of the pressure with a component of thermal conductivity, diffusion coefficient actually. There are some more precise models that try to predict the behavior of the plasma in a more precise way. One of these well-known models is called Brzezinski type fluid model. In this model, in order to get a better description of the physical properties of the system, higher order moments of the fluid are taken into account. But what are these moments? These moments are exactly the same physical properties that I talked about in the previous slide. The density, which is shown with a rho, is the zeroth order moment. U, or the speed or the velocity vector of the fluid, is considered as the first order moment of the fluid, and P is the second order moment, and so on. We can just compute the higher and higher order moments of the fluid, and by including these higher order moments of the fluid, we can get a better description of the fluid. But at the same time, the complexity of the system will grow exponentially. Using these more advanced models, we can also get the evolution equation for all of these moments of the fluid, which are shown as in this slide. In this system, the right-hand sides take into account the effect of collisions in between the particles. But now let's see how the particles are gonna behave in the system and how the collision of the particles is gonna affect the system. We call a system in general collisionless when the size of the system, when the particle collision's mean free path, which is shown with lambda here, lambda call, is far greater than the scales of the system. Vice versa, if this lambda collision, the mean free path of the collisions, is comparable or smaller than the scales of the system, we call that collisional. But why is this important? It is important because the observations of the shocks and the realism has shown us the mean free path of the collision between the particles, which are mostly protons and electrons, is comparable to the scales of the system. As you can see in this slide, the increase in the magnetic field for a shock that is observed, for a shock that is modeled based on the parameters observed for the shock and the realism, the thickness of the shock, which is 0.12 AU, is comparable to the mean free path, the collision mean free path of the particles, proton, electron, proton, and a proton, proton, and electron, electron uh, in this system. So this gives us the information, extra information that this realism can be collisional rather than collisionless. By using these higher order moment models, what we want to do is to try to get a better understanding of the physics going on um, in the plasma in the outer heliosphere in the realism. This is a solution of a solution of a system solved for um, um, the system with higher order moments of the stress tensor and the heat flux that gives a broad shock transition uh, for the parameters that are comparable to those in the realism. The significance and applications of this shock, and eventually the summary of this shock, is as shown in this slide. The shocks that are observed in the realism are different from those closer to the sun, uh, which gives us the motivation that that the dissipation mechanisms are more likely to be caused by the collisional rather than collisionless processes. It is also understood that not only for far outside the heliosphere in the realism, but also even closer to the solar corona, the plasma behaves collisional. So we can use these higher order moment models to study the plasma uh, near the solar corona. Um, so uh, the other advantages of using these models is that we will have a more accurate um, description of the space plasma, uh, no matter closer to the solar corona or in the deeper space in the very local interstellar medium. Um, Thank you so much for listening to this talk, and I hope you have a great day.